start recording. And now we can begin, now that I'm sure that there's no little snafu there. Okay, hello everyone, and welcome to Handmade Hero, the show where we code a complete game live on the interwebs using absolutely nothing, no engine, no library. We program everything ourselves from scratch as basically both for education purposes and for fun, honestly, because I like coding things from scratch. And so today we have something fairly important that we have to tackle, actually. So I don't want to waste too much time before we get right into it. So I will simply say, if you are following along with the code and you have pre-ordered the game on handmadehero.org, you should have gotten a link in your email. In that link, there's a zip file, and in the zip file, there are zips for every single day. You want to unzip day 42 source code because it's day 43 right now, and we always start with the previous day's source code. So if you unzip that into a directory somewhere, then you can start coding exactly where I am coding right now, and so you should be able to follow along precisely. So let's go ahead and get started. Like I said on the when I posted on Twitter today, what we're supposed to do today is we are actually supposed to get ourselves a little bit closer towards having some good player movement code by taking a look at the equations of motion, which are basically the physics that underlie how real things in the world move, understanding them, and then figuring out exactly what part of them we want to use or what we want to do in order to create something that feels good to play, which is not always the same as making something physically realistic. Usually what you want to do in a lot of scenarios is you want to kind of know what the physically correct thing would be, because the right thing to do gameplay-wise is often close to that thing or has a lot of the properties of that thing, because people's brains are obviously attuned to work the way physics works, and to think about things the way physics works is what they have experience with. But it is also often the case that you don't really want a perfect physical simulation most of the time, because we want to kind of go more towards what's fun to control, not what it would be accurate, right? We're not trying to make a simulation here. Some games are trying to be simulation-y, and those games should care a lot about how accurate their physics are. But in our particular case, we're more concerned just with how the player, how sort of that hero character feels to move around. And so in that case, what we really want to do is just kind of know what the equations of motion are in the real world, and then go ahead and take the opportunity to sort of like bend them a little and make up essentially some equations of motion that are whatever we think feels the best just from playing with it. And I don't even know exactly what those are going to be ahead of time, right? We're gonna see by sort of just trial and error what we end up thinking is the most interesting way to have our character be controlled. Now, if you remember yesterday, what we did is we started replacing things with a vector structure that we had. We actually turned it into, just at the end of the stream, we turned it into a union. It's basically just this right here, and all it is it's an XY pair, right, like that. And we then went ahead and made all of our code kind of start working with that XY pair, just kind of sucking that up a little bit, and so made a lot of things that were verbose a little bit more straightforward. And we didn't actually spend the time, because we kind of got to a little late in the stream, to actually condense everything that we could have condensed. Certainly, we still left a fair number of things in scalar, or even though we were doing them in vector, maybe still left the math as two separate things, one for x and y and that sort of stuff. So we haven't done too much work to condense our code, but we did a little. And I don't really want to go crazy with that right now, because we can always do that later, and there's really no particular need to change working code at any particular time. So rather what I'd like to do now is just kind of concentrate on this player P thing here. Maybe we'll think about looking at the camera P as well, but this player P is basically something that we had, which is just saying here is where the player actually is in the world. And what I'd like to do is start thinking about that in terms of how we want to modify it and how we can make it feel a little bit better. So if we actually run the game and just look at what the game has right now, you can see that the character motion, and we talked about this already, just does not feel particularly good. It's kind of, as you move around, you just kind of feel like it's, it's just the most basic thing. It just kind of, it stops instantly. It doesn't have any kind of acceleration or anything to it, or any feel there. It doesn't have any momentum, so when I let go, it just kind of stops immediately. And there's really there's nothing good really about the feel of this particular, about this. And so what I want to do is start to fix that by, let's just, just kind of adding in some basic stuff. give it a little bit of that momentum, give it a little bit of that, like it accelerate and decelerate, just to give it a little bit of that feel. And we don't want too much in that. We don't want a crazy amount of acceleration and deceleration because we still want the player controls to be nice and tight. This is an action game. We don't want the player to feel like it's super soupy and kind of really hard to like stop where they want to stop. But I just want to give it a little bit of something. And so what I want to go over first is just to sort of say what sort of the background is here in terms of what actually happens in the real world in terms of things that are in motion. And so what happens in the real world, right? If I've got something, this is going to be my like magical sphere here. You know, maybe it's a magical sphere with a little reflection on it. It's like a bowling ball or something like that. So I've got my little sphere or something, and you know, I want to start talking about how this thing moves around. Well, obviously, there's some basic things that happen with any physical object in the world. One of them is that it is constantly subject to a downward force, and we all know what that is, right? That's gravity. And gravity is a very interesting kind of a force, actually, which we can talk about a little bit more later. We won't really have to think about it too much for moving the character because he's not really falling. He's always in contact with the ground, and we assume that like the gravitational forces are getting handled by his little sort of stumpy legs things that he has under there that kind of keep him on the ground or whatever. But point being, everything in the world is constantly under gravity. We know this. So there's always kind of a downward force that's at play there. And it's actually more of a downward acceleration technically, but again, I said we'll kind of think about that a little bit more later. We don't have to worry about it too much now. And then anytime that any object is going to move, it's basically the way in which it moves can be broken down into sort of two distinct, I want to say, categories, or two things you have to think about when you think about how an object moves. And when I say this, we're talking about basically, I'm going to just preface this by saying, oops, that this is rigid body dynamics that we're talking about here, which is specifically talking about sort of the way in which matter in the world moves when you reduce it down to the basic concept of just let's assume that all of the atoms and, you know, quantum physics and all of that stuff that makes up my little bowling ball sphere thing, let's take those out of the picture and just say, if we just assume they're all rigidly connected right now, and we're not talking about what happens when the ball breaks or what's happening at a molecular level and all these sort of things, we're just talking about how the gross, large sort of body that these things form move around. There's really two ways that we have to think about that. One is called linear, and the other is called angular, right? And they are sort of exactly what you would think. You essentially have to think about how the thing moves around. So like how, the path that this thing is taking through space, right? How is this thing moving? That's linear, the sort of the linear dynamics of it. And sort of the angular dynamics of it are how it's rotating, right? Because this thing could spin around, right? It could do all sorts of things that induce sort of like a rotational motion, even if the thing is sort of standing in one place, or sort of sitting in one place. Now, the physics behind these two things are not actually different at the lower levels because, again, everything is just a bunch of atoms, everything's just a bunch of quarks, however far down you want to go. And those things all have physics that determine how they work, and they aren't separated into whether the motion of the atom was about the ball rotating or whether it was about the ball moving. So down at the molecular level, it's not going to be about what the bowling ball was doing out where we observe it, right? But in terms of our simulation of it, where we are making this reduction and saying we're not thinking about atoms, we're not thinking about any of that stuff, we're just thinking about it as one sort of gross object, because we are treating it all as one group like that, we have to think about both how it moves in space and how it spins. Because those two things are necessary to figure out where all the atoms actually were when we go to actually say, okay, where is the ball now, right? So what we're going to do today is we're going to focus on this part here. We're not going to talk about this part, which is why I picked a bowling ball, because, hey, a sphere, you don't really care which way it's rotated to some degree in terms of how we're going to draw it. So if we're just moving around, I picked something that'd be nice and easy to think about in that case. So we're just going to talk about the sort of the linear portion of things. We're just going to talk about the movement. And so the movement, basically we have forces in the world. That's like when I go to push on this ball with something, right? When a hand comes in and I just kind of smack the ball, or if something else hits the ball, like another ball comes in here and smacks the ball. Basically, we have forces that are applied to this object. And those forces are all actually acting for the purposes, again, of the rigid body dynamics sort of way of viewing the world, you can think about reducing this object and all of its complexity down to basically just its center of mass. So basically the center of mass, which is if you think about the entire sort of all of the matter that's in this thing, if you think about just thinking of where that's centered, where all of it, if you look at the point that basically, if you averaged how dense it is everywhere in it and figured out the center point of all of that density, you would get the center of mass, which is basically a point which, if our sphere was uniform density, would be like right at the center, right? And again, a lot of this stuff is stuff that you'll only care about if you start to actually do real physics stuff. I'm just mentioning it so you can kind of know what we're talking about, right? So we don't have to think really about densities and masses too much, but it's just something, mass may come up a little bit, but point being, if you're doing full 3D stuff, you would start to care about a lot of this stuff. Anyway, so what we want to think about is we want to think about all of the forces that are applied to our object, okay? So all of these things that might be pushing on our object at any given time. The gravitational part of it, the things that are pushing on it directly, impacts that are happening, those sorts of things. All of these things we have to consider in terms of figuring out where the center of mass of our object goes. And at the end of the day, on any given instant, what we want to do is look at all of these forces and determine, due to all of the forces that are impacting this thing right now, where is it going to be pushed? What is the net sum total of all of the forces on this thing? How is it going to be pushed, right? And now there's a very fundamental equation that you probably have seen before if you took high school physics. Again, it looks like this. It's F equals ma, and what that basically says is force equals mass times acceleration. And the reason that I point this out is because forces, which are the things that push on this ball, right? Wind could be a force, for example. Something directly pushing on the ball. Gravity could be a force on it, et cetera, et cetera. All of them are forces, and the degree to which they affect the ball. Remember, the acceleration is what determines what's actually going to happen to the ball. The acceleration that those forces produce is mitigated by the mass. The mass of the object that's being moved basically determines how much each individual force will actually affect the object, right? So if we look at what all the forces are, and then we want to see how much the sum of those forces will affect our object, we have to think about what its mass is, and we have to solve this equation basically for A, right? So it's pretty easy, right? Because it's just F over, right? If I want to solve for A, all I do is divide by m, and I get F over m equals the acceleration. And that would be the equation for the acceleration. So basically, the heavier our object is, the less it would move for any force, right? Because as the m gets bigger, the acceleration goes down for any given force. And that's exactly what you see in the real world. The heavier something appears to be to us, the harder it is to push it. That's just the intuitive way to think about this, right? There's a lot more involved there, but that's basically an intuitive way of thinking about it, right? And so, if I want to start talking about how physics actually works in terms of how it affects something like a rigid body, like a bowling ball or whatever it is, or our little guy there, essentially what I want to do is I want to talk about summing all the forces on him. I want to talk about computing what the acceleration actually is for all of those forces combined, right? And so I do that by figuring out what the mass of the guy is, and I do my divide, and I get out an acceleration. And then, again, I have to figure out how to relate this acceleration back to a position, right? Because what I want to know at any given time when I need to render this bowling ball, or whatever it is that we're simulating, I have to know where in the world it is. That's like the primary thing I need to know in order to be able to display it on the screen. It's also the primary thing I need to know to be able to do collision detection or anything else. I need to know what that is. And so that's where we get to sort of the hierarchy that you've probably seen before, hopefully, but maybe not, but position, velocity, acceleration, right? And this is what I talk about when I say the fundamental equation of motion, the very simplest stuff that moves things around. It's a hierarchy that looks like this, and all of these things are essentially dependent on time, okay? Physics is all about what happens to things over time, and so when we talk about doing sort of rigid body dynamics or physics or anything sort of the thing, we're talking about looking at this hierarchy of information about one of these objects that we're moving around or doing whatever to. We're talking about looking how these three quantities change over time, and these three quantities are all related. If I want to know, if I say that I have a function for an object's position, then these three are related very simply. The first derivative, if you remember your high school calculus, the first derivative of the position is the velocity, and the second derivative, right, of the position is the acceleration, okay? And so that is, you know, like, again, these are just the fundamental equations that govern how things actually work sort of in the simplified representation that allows us to just consider entire collections of atoms, if you will, to act as one. And so this, it may look a little daunting because like he's drawing these f of t's up here and he's got all this stuff and there's time and I don't understand what's going on. This is getting confusing. But it's actually relatively straightforward and I can kind of relate it back to what we're doing in the code relatively simply. We already have one of these things in the code, obviously, right? We already have position. Because I just pointed that out to you. That's right here. That's our player P. And we know this is our update loop. This is how player P gets updated. What were we doing, right? We took the player position. We multiplied by however much time we wanted to advance the delta, the difference, like however, you know, the motion, basically, that we want this guy to take. And we added that in to wherever he already was, right? And so if you think about what that's doing, okay, yeah, again, going back to our sort of vector representation of things, if the guy was here, right, and this is my position, so this is my position right here. If the guy was here, what we're essentially doing is we're saying we have a direction that he's going to go, right? That's our D player right there. And then we're multiplying that direction by the time, by dt for frame. Now, why did I call it dt? Why did I call it dt? Well, it stood, and I didn't actually say this at the time because we weren't there yet, it stands for delta t. T, obviously, is time. Delta t means the difference in time, right? It's the difference in time between 2 points, last frame and now, or in our case, since we're doing it slightly differently, we're actually doing it the difference between the start of the frame and the end of the frame. We're like sort of thinking about it in that sense. So we're saying the frame, the stuff was here, and now it's going there, and while the frame is up on the screen, we're imagining the objects to move from one place to the other over that time step. So if we were going to do motion blur or something, it would be across that time step, if that makes sense. So there you go. So that's actually what we're talking about here, right? And that's what we're doing when we actually do this update. We're taking a direction, we're multiplying it by delta t, and that's how far we're moving him, right? Now remember, I believe we talked about this a little bit. No, I guess we didn't really talk about this too much. So I'll mention it today because this is actually relatively important. We talked about scalar multiples of vectors, right? We basically said that if I have a vector, you know, I could multiply it by some scalar, like I've got a vector here, I could multiply it by, say, 2, and I would get a vector that's twice that length, but pointing in the same direction, right? And what I don't think I ever actually said was you can consider vectors as having a magnitude, right? We could consider vectors as having a length, and we did a bunch of that stuff yesterday. Remember, we were doing the Pythagorean theorem and stuff, and we were looking at how long some of those vectors are. So basically, from here to the tip, you know, from the base to the tip of the vector, right? That's a particular length, and that we call that the magnitude of the vector, right? So you can think of vectors as having a direction, which is sort of the line along which they're pointing, and a magnitude. And that direction is actually signed because it's either pointing positively or negatively in that sense. And then the magnitude you can think of as how long it is in that direction, right? So that's just something to keep in mind. So again, what we were doing when we were actually computing the update for our guy is we were taking sort of a direction, a place, you know, a sort of a line in which we wanted him to travel, which we had set up here using what keys were down. And then we said, we're going to move him as far along that direction as there is time in the time step, right? However big the time step was, that's how far along the line we're going to move him. Now, the time step, of course, is in seconds, and it's going to be some fraction. It's going to be 0.0 something seconds, right? 0.033 seconds or something like that, because we're at 30 frames a second, so the amount of time between 2 frames is a 30th of a second. So basically what we're doing is we're taking the vector and we're making it have magnitude 0.033 if the vector was unit magnitude. Now, the vector isn't actually necessarily unit magnitude, although I think it always is. Am I right? Yeah. So we always are actually setting that vector, you can see here, to be a length of 1, right? It's going to be 1, -1, or 1. It's always got 1 as the magnitude. And in the case where we were going to move both axes at the same time, we solved the Pythagorean theorem to see what that distance should have been in order to reduce it down to being the same as it was here, which means this is actually also going to produce a vector of length 1, which is kind of amusing when I think about it. So yeah. Oh, okay. But we do one thing here, right? We've got one other thing in the mix. And in fact, I think I'll move this down below here just to make it clear. So then what we do beyond that, now that we actually know, okay, that's how we now have a vector that's sort of magnitude 1, we then said we have a speed we want the player to go at, which is going to be 2 meters per second, right? Because our world units are meters, and we're talking about how fast this player is going. 2 meters per second, or if I have the special magic button down, it's 10 meters per second. And then we were multiplying the vector by that. So we actually already did another magnitude scale here. We took a unit length vector, one that's only 1 unit long, and we multiplied it by this to get a vector which is that long. It's going to be a vector that's 2 units long or 10 units long, depending on how far, depending on whether that button was down, right? And then when we actually go to move the player, we multiply that total vector by however, which is this right here, by however much time we want to advance. So this is essentially, that means this vector, if you think about what its units are, this vector is the amount that the player would move in 1 second. Because we're multiplying by fractions of a second, right? So what we're essentially doing here is this is meters per second, right? We're multiplying by seconds and just getting meters out, right? Again, dimensional analysis. So these are meters per second units, if that makes sense. This is in seconds, and so out comes meters per second. And again, we've kind of been sneaky about it here because we never really came right out and said it, but what we were basically doing is we were doing all that essentially with vector math. We were saying we want to make a vector that's going to represent his movement, and we want to represent the movement cleanly, so we can just say meters per second, which you'll note doesn't have a direction to it. This is just 10 meters per second in some direction. And we let the fact that we have a unit vector pointing in the correct direction tell us how to construct the motion in x and y that actually corresponds to this speed along that line, right? I know it's a little confusing, but I just thought I'd point that out just really briefly. Okay, so we can go over this again in the Q&A if it's complicated. I know there's a lot of concepts here, but point being, that's what's happening, right? We're basically taking a position where we're starting, where we've got a direction, and then we're trying to make the magnitude of our resulting vector that we're going to move by be proportional both to how much time has elapsed and how fast the player is going. So we have a speed in meters per second, we have a time in seconds, the seconds cross in dimensional analysis, remember, so they go away, and we're left with just the meters. We advance the guy by the meters, and again, it's all in vector, so it's got a direction, it knows what direction it's going, and it knows how far to go, and boom, we get to our new position. That's what we were already doing. Now, what is actually going on there, right? Well, we know that position is measured in meters. We already said that, right? We already said that position is in meters. Well, what is this meters per second, right? So we did seconds, we crossed out seconds, right? We basically said, let me write this equation actually explicitly over here. We actually said, right, we said we have delta t seconds times whatever our player motion is. So our player motion amount, motion or whatever you want to call it, meters per second, right? Like this. And I crossed out those seconds and I got meters. But what was this sort of motion meters per second weird value that we were multiplying here? We know this is a time step, right? We know delta t seconds is a time step. But what was this nonsense over here? Well, that's actually the velocity, right? Meters per second. It's how many meters somebody goes in a second. And that is exactly what we were doing right here. We were actually doing a velocity-based update of the position of our guy. We computed the velocity to be dplayer, which is either a 2 or 10 unit long vector pointing in the direction the player is going. We multiplied by the dpt per frame, which basically gave us how much to move the guy in position space for that time step. That's basically integration. We integrated a velocity up to a position, right? That's integration. Integration goes this direction, right? This is a high school calculus again. Integration goes up, derivative goes down, right? And so we've already performed an integration, you just didn't know we were performing it. And that's not really particularly surprising. Because if you think about what happens here, right? If you want to integrate a very simple constant quantity, you just have some motion that's not at all dependent on time, right? If you just have to integrate 2 meters per second, right? Then obviously the integration for that, if you remember your high school calculus, is just multiplying by whatever the change is, right? Delta t is exactly how you would integrate that up to position, right? That is basically a discrete integration up to a position. Now I'm running out of space here on the board, which is unfortunate because I'd like to keep going, having these things around, but well, I can't. What can I say? So let's think about this a little more explicitly, right? Let's think about position, and that's my f of t. I've got velocity, which is my f prime of t, and I've got acceleration, which is my f double prime of t, right? Now, I'm just going to write down basically what you probably remember from your high school calculus class, and then I'll sort of come back to what I was saying just a few seconds ago and kind of try to tie it up a little bit just to make it a little more solid, right? So if I have some function of position, right? I don't know what we want to say that it is. I don't know. Let's say that we just had some function of position. So we have our f of t. That means we're going to plug into t. We want to get a position out. Whatever it is, right? I could say that that was something like 5 t squared, plus 2t plus 3, right? This is, again, standard old calculus stuff that you might see, in a textbook, right? And we all remember how you would do the derivatives, right? If you want to take the derivative of that function, you do this thing where you take the exponent of the variable, you multiply it by the front, and then you reduce it by 1, right? So you'd end up with 10t, right, plus, again, this one doesn't have 1, so this is just an exponent of 1, so it's just going to remain 2, and then I reduce it by 1, that gets t to the 0th, which is nothing, and then this guy doesn't even have a variable, so he ends up getting knocked out entirely, so he's just gone, right? And so we end up with something like that, and that is the velocity of this thing, right? Now you may ask, like, I don't understand, what are we talking about here? And again, you can think of these just as just think of these exactly what we were doing here. Remember, we had the x and the y written out separately. Think of these as the x's and the y's written out separately. This is the x coordinate of our guy. We just had a function that we said, we said he was on rails. So as time increases, he's just at this x coordinate. We just compute it, and that's where he's at. And we want to know what the velocity is, right? So we want to know what the derivative is. We want to know how fast he's going. So this is our velocity. That's how fast he's going. That's how fast he's going in x, right? It's his meter per second. That's what that is. If we want to know his acceleration, we can take it again, right? We just go down one more time. And again, this guy drops out. This guy is removed completely. So we're just left with 10, right? And that's just directly what the acceleration actually is, right? Now, what I hope you can see here is these relationships are actually very simple. And if, for example, right, I wanted to know I wanted to be able to do this discretely, right? Because what you can think about here is this is all well and good, but it presupposed that I could write an equation that's the location of my guy. But I can't write a location that's the equation of my guy. The user's like entering, commands and stuff. He's telling me where the guy moves every frame. It's changing and all this sort of stuff. So I don't have the luxury of just writing out some specific equation that says where the guy is for all the time in my game, for any time step, at the first second, third second, fifth second, whatever, right? So what I need to do is I need to move from sort of the way that you think about it in high school calculus class, which is perhaps not very useful, even though all the tools are there, right? I just need to start thinking about this in terms of doing it discretely, so that instead of actually trying to make a function, I'm just going to say we're going to discretize it down to one time step, right? And so if you think about it, here's our game time again, like we always say. I've got time equals, this is frame 0, this is frame 1, this is frame 2, this is frame 3, this is frame 4, right? And so in time, in t, this is in frames, right? In t, we've basically got time 0, time 0.033, repeating 0.066, so on, right? This is what the t variable is. if I was lucky enough to have somebody who was always moving based on just a fixed equation, right, I really wouldn't have any work to do. All I would do is just take that equation, and wherever I was in time, so I want to draw this frame, I just go, oh, 0.066, I plug it in here, and I get the x-coordinate out. Done, right? No problems. But we don't have that luxury because the user is inputting stuff and all this sort of thing. And so there is no constant equation that we can just use all the time that will give us back the location of the guy. So what we need to do instead is switch to something where we're essentially discretizing these equations of motion and pretending that the equations of motion are essentially constant over the time step. Meaning we're pretending that the guy is just going to move in a line over the time step, and you know, the time step's going to be so short that he appears to like curve and do stuff, right? On when he's actually when you actually see him, he appears to be changing direction and doing all these things because over time you're changing your inputs and all this stuff. But really, in any given time step, what we want to do is discretize it down so that we're basically just taking the input that you gave and applying some piecewise function, the function that only is going to operate over that time step. And then on the next frame, we will essentially be using a different function, right? Which is a different, responds to the keys differently, right? And when I say function, I don't really mean much of a function at all. I'm just talking about a very simple function that's like we already had, where we have a vector direction, and we're going to basically pretend that the guy is moving along that vector direction by delta t, right? Or something like that. So very, very simple version of the function. It's nothing complicated, nothing too interesting, right? So in order to discretize this, I guess what I would say is, so you know, hopefully people are comfortable with how to take a derivative and what we did here. And basically what we want to do is say, okay, let's just assume, right, that at every frame, we're going to start down here with a constant acceleration, and then we'll just integrate it up, right, to get our velocity and our position. And we don't care about the fact that, you know, each time we integrate it up, we're essentially creating a totally different function with different coefficients, right? Because if this frame it's 10 and the next frame it's -5, we're going to get completely different values when we do the integration up, right? But we don't care about that. Like I said, we're just going to say for each frame, we're going to pretend that we have a different, essentially a different set of coefficients, if you will, in our function here, right? So really, there isn't a whole lot to this. We already did the work. You can read it right off of here, even if you don't know how to integrate. If you just know how to take derivatives, you've already got the answer, like, because we're looking at the answer right here. If we wanted to say we want a particular acceleration on every frame, well, here is that acceleration, right? It's 10, right? That's the constant acceleration. So let's just replace that constant acceleration, right, with whatever we want the acceleration to be, a, whatever we compute it to be, okay? We then say, all right, our velocity is the first integration up from that. The 10, remember, comes from here. So this is actually going to be a, and it's a times our t, right? It's times whatever the time value actually is. And then we do plus 2. What is that 2, right? What does that 2 actually mean? Well, the 2 is essentially the existing velocity, right? It's saying this was the part that accounted for the acceleration, the change in the velocity, right? Because it's multiplied by t. So over time, this is changing our velocity. This is the constant velocity. So this is whatever velocity was on the last frame. This is what we're coming into it with, right? So this is just our v. That's our v term. So at plus v is actually the term that we want to use for our velocity, right? And then finally, when we get up here, you can see that we get integrated up one more time. This plus right here is just the existing position of the guy, right? This, we're adding a new position for the guy. We're taking his old position and updating it. So this constant that was in here before is just wherever he was, right? There's the p, right? This guy right here is the velocity again, right? That 2, that was the 2 from right here, right? So that's just the v. And then here you can actually see, and again, this is why I say even if you don't remember how to do integration, you can cheat it by just doing the derivative and then doing it backwards. Remember how we got this. We did 2 times 5, right, equals the 10. So all we have to do is divide the a by 2 to do our final integration, right? That's why this was 5 instead of 10, right? So instead, we just have a over 2 plus v plus b, right? So what does that actually give us? That actually gives us the final, if I just read these off and get rid of the scribbles, right? That basically gives us that our top equation for motion is, 1/2 a times t squared, which is this term right here, right? Plus v times t plus the old position, right? So whatever the old position was, yeah? And again, this v is actually the old velocity as well. The velocity, right, whatever, and so this is our new position. This is our, and a lot of times we do p prime for that, so you don't have to keep writing old. You just assume that these were the old ones. P prime is the new position, so we just have p prime equals 1/2 at squared plus vt plus p, right? And so if I want to know p double prime, or basically the new velocity, right, v prime, then that's just this equation. That's at plus v. And then finally, if I want to know the acceleration, it's just prescribed. So basically, there is no new acceleration because we never saved the acceleration. So there's just acceleration that we specify, and now we can specify whatever acceleration we want, and we can compute any of the quantities that we actually wanted to compute. Now, you will notice that these things basically don't even really imply all that much more stuff than what we were already doing, right? Essentially, we just didn't have these terms, okay? We had this. That's all we had, right? If that makes sense. Now, I haven't really talked about the delta t part, but just bear with me for a second. There's a lot of stuff to cover here, so I'm trying to make it, let's see how much we got. Whoa, ooh, we're tight on time. All right, so if you take a look here, we already had exactly that top equation minus the acceleration, right? We just didn't have an acceleration in there. We had whatever the dt was times the velocity that we wanted the guy to go at, right? And so that was this. That's the velocity times the time plus the old position. Velocity times the time plus the old position, right? So we were already computing part of this equation, and your intuition when you're writing a game code, even if you didn't know any of this stuff, is to write that, right? That's what you would write, and that's what we did write. So really the only thing we have to start doing now is thinking about this other part that's maybe not so intuitive, which is that there's another quantity here which gets accumulated into that velocity. So the velocity is now something that actually needs to be stored from frame to frame so that we know how fast something was going, so that we can update it with our acceleration every frame and then integrate it into what we think the position should be and so on. And similarly, in order to properly account for the effect that the acceleration has, we want to put it in this equation as well. We want to put it in this part of the equation here, the 1/2 at squared, to account for the effect that the acceleration has over this time step as well, right? Because without this, essentially what would happen is we would be assuming that acceleration was not actually continuously happening over the course of the frame. Now, we could argue which one of those we'd rather have, whether we want to have an instantaneous acceleration, which is what would happen if we didn't do it this way, right? Let me explain this in a little more detail. There's two ways we could have chosen to program this. One is to do this step first, right, and use v prime here, okay? Do you see what that would do? That would still get us a t squared for our evaluation because basically this at is baked into here, right? This term, right, which was normally vt, which is the old velocity times time, which just says that velocity is carrying through from whatever it previously was, it's carrying through this frame, right? If I change that to v prime t, well, v prime t is this, right? So if I multiplied that out, I'd get at squared plus vt, which is close to this, but not quite because there's that 1/2 in there. So essentially what happens is that 1/2 is counting for the fact that the acceleration is being evenly distributed across the time step, not instantaneously applied at the beginning of the frame. And so it is technically more accurate to do it that way in terms of what you were trying to actually simulate. But what we have to also acknowledge here, for anyone who wants to write it the more simplistic way of just doing this and then using v prime in here, is that we're going to hack all these variables anyway. We're going to tune all these variables to be stuff that feels good to play. And so at the end of the day, it's hard to get too pedantic about it and go, well, you got to do your 1/2 at squared, and if you don't do 1/2, you're not doing it right or whatever. It's hard to to really make that argument, right? But what I will say is, if you want to do real physics at some point, you need to start sweating those kind of details, because things start to get much more important when you're not hacking a bunch of variables to just make the guy feel good or whatever, and you want to actually try and get realistic, believable behaviors out of certain physical properties and that sort of stuff. So it's good to know what the equations are and how they work before you start short-circuiting them, so that you don't end up at a limit where you can't get past something and you can't make something feel or work right because you've forgotten all this stuff and been sloppy, right? So it's good to know the rules and then break them, not just sort of go willy-nilly about it. So I just want to kind of point that out. Okay, so finally, really quickly, and maybe we'll have to go over this again tomorrow because there's a lot. I had to talk a lot to sort of talk some of these things out, and I feel like a lot of it's just very detailed and tough perhaps to absorb. But anyway, what I did want to say is, where does delta t come in, right? Because those functions that I wrote over there, they were continuous functions. So when I said 1/2 at squared, right, plus vt plus p prime, when I said that, that's just a function where you plug in a t, right? That's a function where I just plug in some t value and I get the position straight out, right? So what's going on here? And the answer is, well, remember, what I said we were going to do is treat these functions as if they only exist for the time step, right? So effectively what we're doing is every frame we're creating a new equation of motion where we specify a new acceleration, integrate it up twice to get our equation of motion that will store our new velocity and our new position, right? And so really, this is f of 0 at the beginning of a frame, and f of delta t, however much the frame time is here. Then on the next frame, we're going to do the exact same thing again. Pretend this is f of 0, and pretend this is f of delta t. And what do we want to know? We want to know where the guy would be at the end of the frame, right? So if we want to know where the guy would be at the end of the frame, well, that's delta t. That's what we would plug in. So we plug in delta t to our function, delta t, and that's why everything is in terms of delta t. It's because really delta t is the time at which we want to know. If we wanted to know where the guy was at the beginning of the frame, we could still use the same equation. It's just all of these terms drop out, and we just get p prime, right? T squared, if delta t, if we're plugging in 0 for this, if we're saying f of 0, that drops out because obviously 1/2 a0 is 0. Same thing with vt. If t is 0, the v drops out, and we're just left with p1, which is exactly what we would expect. If we haven't gone anywhere in time, we would expect the guy to be wherever he was at the end of the last frame, which is p prime, right? So again, what we're trying to do here is we're just trying to put together piecewise functions that get us from one frame to the next, and we restart the function at the beginning of every frame, right? So it goes from 0 to delta t, 0 to delta t, 0 to delta t, right? Now that's not to say that we couldn't have some object that does have a function that it uses across many frames. That's totally something we could do if we wanted to. It's just that's not something that's particularly useful for a guy who's under player control, because when you're under player control, you really do restart your acceleration every frame, and you're getting basically a totally different function. It's not some smooth continuous function that can be mathematically analyzed in that way. It's piecewise, is what it's called, right? It's a piecewise function, which means, a normal smooth continuous function looks like this kind of thing. A piecewise function is one that's like that kind of thing, right? And it doesn't actually have to be lines in between there. It could be, like this. It could have curves, but then the curves have sharp bend points, right? And that's why they call it piecewise, because there's basically, it's pieces, right? Little individual segments. And basically that's what we're doing with our stuff now. Okay, so very quickly, we don't have very much time left, obviously, because I had to sort of yammer on at you about those things. What did I actually need there? Well, remember, I need a velocity. I need to store a velocity, right? I need to store, and I usually use d, that's what I use dd to denote accelerations. I use d to denote, I use dd for second derivative, d for first derivative, right? So one of the things I need to do now is we were just working with a velocity that was just only existed on that frame. We need to start storing that velocity, because remember, the old v came into play there, the old velocity, so we need to start storing that from frame to frame. And we can assume it starts at 0. That's totally fine, because obviously we know that the guy will not be moving at startup. He's just staying where he is. And so then what I need to do in here is I need to start thinking about this in terms of his acceleration, not his velocity change. So what I'm going to do instead here is say that this D player, right, that we're actually doing here is actually DD, right? So D player is going to become the DD player. So that's actually his second derivative of his position, right? And so now what I'm going to do, I obviously still want to compute, I want to compute those equations of motion the way that I said I wanted to on the thing. So again, we have, let me write them out for you again. So again, we have 1/2 AT squared, right, plus VT plus old prop P, right? That's our equation for, I'm sorry, there we go. That's our new position, right? And we have, for our second derivative, right, or our velocity, our new velocity, we said that that was just going to be AT plus the old velocity. And similarly, the acceleration, right, is just specified. We don't have to do anything about that. We're just specifying it. The user is basically, this is coming from the D-pad, right? The user is saying what that acceleration is. Okay. So we want to actually just compute that, not too hard. 1/2, right, A times T squared. So I'll go ahead and say square. We need to write that. We haven't written that yet. So that's literally 1/2 AT squared, right? I'm really just literally typing it in. Then I want to do the same thing for the VT, right? The VT term. So that's here is his velocity. His velocity is the game state D player. There we go. Times that delta. So there's T. And then I just need to use his old position, which for, just to make it totally clear, I'll put it in there and change this to an equals. So that way it looks exactly like the equation we wrote. 1/2 AT squared times plus VT plus the old position, right? So that's the update right there, very simple. And the other thing I can then do is say I'm going to change his velocity as well. And so his velocity, and there's a couple things we want to actually talk about here. So the velocity update is going to get a little fancier than this potentially because of when the player is colliding with things. But for right now, let's ignore that so that we can, because we don't have a lot of time, like I said. So we'll kind of do a more straightforward version. So to update that velocity, to give him his new velocity, again, it's really simple. It's just the AT plus V. And so I literally type that in. There's my A, right? There's my T. Right, and then I need my old V, which is this right there. Okay, and so that's pretty straightforward. There really isn't all that much to it. That is the entirety of the actual code that we would need to do the update. So all we really need to do now is actually create that DD player correctly. And so we could probably just leave it as it is right now, which is to say that he accelerates at 10 meters per second squared now, right? Because again, this is an acceleration, so it is now no longer meters per second, it's meters per second squared. That is just sort of taking the derivative in time space, right? Because remember, t, we are not taking, it's important to remember, we're not taking a spatial derivative. We're taking a derivative with respect to time. And so basically we start off in meters, we get meters per second, and then we end up with meters per second squared all the way at the bottom. Time is the thing that's increasing in order of magnitude in power here as we take that derivative. We are never actually changing the meters because we're not taking a spatial derivative. We're not trying to ask how these equations change when we move around. We're trying to ask how we move around based on changes in time. And so that is why you notice the meters doesn't change. That's kind of a topic for another day, but point being, just thought I'd throw that in there. Anyway. So we got our acceleration now, and in theory, I think actually that was literally all the code that we would need to write to give our guy momentum. But we need to write that square function. So in my handmade math, I'm going to go in here as well and add a little squaring function. A squaring function is just one that takes its value and returns it squared. The simplest possible thing you could imagine, right? A times A, and there we go. So that's just a way, and why do you do that? Why not just write A times A? Well, it's a little bit easier. This might be a whole expression sometime, right? Like, right, or something like that. And you don't want to have to type that out twice because you might make mistakes. So it's nice to have a little squaring function that you can just use to save on the typing. Oops, that's D player P. And there we go. So I believe our guy, we probably have too slow of acceleration now. I don't know if we do or not. Oh, no, there we go. So basically our guy now has momentum and he behaves exactly as you would expect, kind of like, for lack of a better term, like a hockey skater, right? Because remember, we've done no friction on this guy. So now he is essentially, he's an asteroids guy. He's floating in space. He has no particular friction. But as you can see how trivial that was, and now he behaves exactly as you would expect a physical object with no friction to behave, just because we spent the, what is it, 5 seconds? I mean, I had to explain it to you for 45 minutes, but once you actually know what it is, you saw how trivial that was to type in, right? Now we've got the correct equations of motions for the guy, and it already feels kind of fun to drive him around. This is kind of ridiculous. And so now you can actually see already the thing I was talking about when I said we have some decisions and some interesting stuff we have to think about in terms of his velocity. When he comes in here and he sticks on that wall, right, our collision detector isn't letting him go through the wall, which is good. But we're not changing his velocity to be 0. We're just storing his velocity as if it's still fully accelerated in that, fully going that direction. Which means if I push the back direction, I have to push for a while to accelerate him up, right? And we could actually, if we wanted to, we could probably do something where we actually showed what his velocity was. Maybe that'd be a good idea to do in sort of quickly at the end of the stream here. And so what we probably want to do, right, because that doesn't feel very good for the player to get stuck against the wall, what we probably want to do very soon, and I don't know if it's going to be tonight because we're mostly out of time, but we want to start thinking about things like, obviously when we do the friction and stuff, we also want to think about things like updating velocity so that the velocity is actually what his velocity turns out to be after collision detection is done, stopping him when he runs into walls and stuff, because that seems like a much saner thing for the player to deal with instead of having this hidden pretend velocity that it doesn't really represent the velocity of the sprite on the screen, right? So that's it. That's really all there is to that. So now, if we wanted to, right, we could do something where we introduce some kind of friction as well to the dude, right? If we wanted to, right, we could say, as he's running around, he gets some kind of a friction that's based on his velocity, right? And I remember we mentioned drag as well was another thing based on the velocity. And so I don't want to try to get into ordinary differential equations, obviously, at this point, especially not with only like 10 minutes left in the stream. But if we wanted to right now, we could totally make it so that this guy actually had some friction by doing a sort of like approximated friction that doesn't actually quite do exactly the right thing. So I'm going to go ahead and set our looped live code editing up here. I'm going to have him kind of go this way, and then come this way, and then come this way again, like so, and then have that go, right? So I'm going to let that guy run there while we make our modifications. I'm going to go ahead and set him up over here, and then I'm going to open the window. I'm going to go ahead and do something I haven't done before, which is delete this window, and then actually kind of come over here and do that. All right. So here we go. So now what we should be able to do, right, is we can see that he's really swimmy. Like you can see how swimmy it is for me when I was controlling him. He kind of swims back and forth. And so I want to go ahead and add some kind of a function in here that's going to reduce his speed based on how fast he's going. So the faster he goes, the more it will push back against him. So like a friction force or a drag force, that sort of thing. And so again, I can't quite do this exactly correctly because we're going to need ordinary differential equations if we actually want to make something behave properly. But for now, we can hack something in. And so I will say, oh, and you know what? We did fix the diagonal will be faster problem. We just didn't quite do it the way that we said we were going to do it. We'll do that eventually. Anyway, so to do ODE here. And so maybe we'll talk about that soon. But anyway, so what I want to do here is I want to say, okay, let's apply that friction force. Now I know how fast he was going on the last frame, obviously, and I also know how fast he's going on this frame. And so the question is, I guess, which exactly one do I want to use? And this is where, if you were using the ODE, it would be correct, but we're not actually going to do that. We're going to do the hacky version. So I guess I'm going to use the old one, the one from last frame. So what I want to say is his velocity, I'm going to basically say his acceleration. You know what, I shouldn't do this here. I can just put it, I'll just pack that in acceleration. I'm going to say that there's another force acting on him. So basically his DD player, right, his acceleration. I'm going to go ahead and say I want to add into that acceleration right here. I want to add in a force that's going to counteract his velocity. So basically I'll take whatever his velocity is, and I'm going to, say that he's going to accelerate in the opposite direction of whatever that velocity is. And for right now, let's even say that it's the full magnitude of whatever the velocity is. So you remember, this is our acceleration. So I'm just adding in an acceleration that's in the opposite direction of the direction he's moving, right? And so I'm going to save that, and we'll go ahead and compile that. I don't know why it decided to open that window. That's probably the least useful thing it could have done. There we go. So that looks a little too strong, right? As you can kind of see when you're looking at how he's going, it just looks a little bit too strong. So maybe I'll chop that down a little bit. Let's say 0.5, right? That looks a little bit better. You can kind of see, right? He can do his turn pretty good now, right? So that seems like a pretty reasonable coefficient to use there. I don't know. Let me jump back in and actually drive him around. Yeah. Yeah, that feels pretty good. Yeah, that's not bad. Now I feel like he's still a little sluggish, though. So I kind of feel like I want him to be a little bit. I think maybe this acceleration is a little too slow. So I'm going to jack that acceleration up a bit, and then maybe I can make this guy a little bit higher. Let's find out. Oops. So you can kind of see that it even starts to look better, right, as you're doing that. And now I can make this dude a little bit stiffer as well, right? He can sort of be a little bit higher because now I've got more acceleration to counteract it, right? Yeah. So it's feeling a little bit better. It's still a little bit, and again, the higher I crank these two values, the stiffer that, the more that there's a counteracting force and the more that the acceleration pushes against it, the stiffer that return to zero is, essentially. If that makes sense. So if I cranked this up pretty darn high, right, and then did that maybe, I don't know. I'm just totally playing around with this just to see. You can see that he gets a nice fast stop there, right? I think I'm going to give him even a little bit faster than that. So let's go ahead and jack that to 2, right? This is why I said we're totally gonna just write whatever random numbers we want in here as we tune it. So you can kind of see he's already starting to feel a little bit better in terms of that that sort of stopping behavior. All right, I'm gonna give him maybe 1.5 is the jackpot for tonight. Again, we don't really want to spend too much time on this because we're gonna change a bunch of stuff. So now he feels pretty nice. Like I could see playing a game with that behavior, right? I could see that being just enough swimminess to feel good, but not too much. It might be still a little bit. There's a lot of things I'm going to want to do to this eventually, let's put it that way. But, for now, that's certainly fine. And of course, now I can sort of get him as he goes through here. Now, what the other thing is, I can also still keep my acceleration key, I suppose. I can make it so that, he gets a nice big speed boost. Whee! And of course, since we did all that through the acceleration, that even keeps his momentum and everything, which is kind of nice, right? Yeah. So it's all good. We still haven't fixed the collision detection. The collision detection is still a mess, so that's no good. But wait, why is our? Oh, there we go. I was like, are we not? I thought maybe I broke something because he wasn't walking off the screen there. But all right, there we go. Yeah, so that's pretty good. All right, so I think that's good enough for today. Obviously, we've got a lot of stuff that we'd want to do to make this more interesting, and so I think maybe, but that's the basics of the equations of motion, and I think they are relatively straightforward once you start playing with them, certainly. We'll continue to talk about them more as we go. Now, one thing I did want to mention just really quickly that sort of kind of came up at the end there, and I just don't feel like I really set it up enough for you to make it interesting. Here is, again, why vectors are so darn nice, and why I said I wanted to get a little simple vector struct in there for us to work with before we actually did any real player movement code or anything. You notice how easy it was for me to slam this correction in here, right? To just say, I want something that's going to be a friction force that acts against the player's motion direction. Well, before, we only had, when this was all doing X's and Y's explicitly, it would have been much harder for me to start thinking about, okay, there's two different directions that are happening. One is the direction of motion. The other one is the direction that's the opposite of the direction of the velocity. Like, all of that just totally I didn't even have to think about, because I can just go, this is an acceleration that has a direction. It's a vector. It knows directions already. So I can go ahead and just add more vectors in here, and it will automatically figure out what the new composite direction is, given the fact that it was adding two different corrections in for the acceleration, one that's about what the user's pushing and one that's about the friction. And it kind of just allows you to sort of smush all this stuff together. Vectors allow you to keep adding that stuff in there. And so again, it's really nice because I can basically say, okay, I've got my acceleration for the player. I started out having the direction that the person was pushing, but then I added the force that was counteracting some velocity you already had, and that gave me a new vector. And then I did some other stuff, like with the collision, which trimmed it down to here or whatever. And the vectors just store all that and track all that really nicely. And the fundamental operations on them look intuitive. Like, hey, look, I'm adding the negative of his velocity, which acts against his velocity, right? It does exactly what you would think it would do. And so vectors just really help you here, because if we did all this in scalar, it would just get so intractable so fast, and we'd have x's and y's all over the place, and we'd be like, right? And so that's what's really nice about that. So I will stop talking about that now, and I will go to the Q&A. So starting now, please type in any questions that you have with Q:, and then the question so I can see it. And please keep whatever you ask to stuff that we did on today's stream or previous streams. If you want to ask an off-topic question, there is plenty of time for that, but we do it in the pre-stream. So we do it come about 15 minutes early from the scheduled starting time, and I answer whatever random questions you want at that time. So if you do have random questions and off-topic stuff, I will answer them. I just want to answer them in the Q&A here. Let's see. So why use real physics instead of something more custom that can be hand-tuned? Well, we are using something custom that's hand-tuned, right? I mean, you just saw me hand-tuned it, right? We didn't try to go measure anything in particular, right? We didn't try to make this accurately simulate the motion of a human or anything. So the reason that we started with the physics equations is because, well, and you know what? This is actually a pretty important point. So let me really say this rather forcefully, actually. I try to keep game design opinions roughly out of the stream as much as possible, but I feel like this one kind of transcends game design and is more about just good programming and good game development. And that is, so many games that I see that are especially indie games, because they maybe are programmers who don't have as much experience with physics or whatever, they feel awful to control. And they had, it was something custom that they just typed in and that they just, tuned for whatever that definition is. But because they don't have perhaps the background or know the fundamentals of how physical objects work, they're never really able to get things feeling that visceral physical feel that you only get from starting with real equations of motion and then tuning them into the position that you actually want them, which is not to say that they're going to be accurate, but having the full power of real physics behind you, knowing what those equations are and only violating them when you think you should, yields a game that just feels so much more natural to a person's brain, because all the stuff they expect to see happen to objects does happen to objects. Like if someone's trying to do a jump and it doesn't happen in a parabola style shape, it's a lot harder for them to intuitively understand how to make those jumps, right? And so a lot of times, like, you want to start with that basic concept so that the player has a leg up on understanding it and using it. And then when you want to add air control and you want to add, whatever, the double jump thrust or whatever, that's all great and you should do it. But you should start with the basics so that people's built-in understanding of how to predict the motion of objects, which has been hardwired into their brain from birth, isn't always having to do other stuff to sort of compensate for the fact that you weren't giving them the baseline that they probably should have for playing the game. And in our game already, we have one of those which drives me insane, and that's the wall stickiness thing, right? When I see that happen, it just feels awful. And so that's like the very next thing on my hit list, right? When I think about what I would want to do here, and again, it may not actually be the next thing on our hit list because I try to structure things in like educational order, not in when I absolutely think I would go do them because they drive me nuts order or whatever. that drives me nuts. And so what I want to see happen there is I want to see a little bounce, perhaps. I want to see a nice smooth glide along that. You know, I want to have a real nice feel for when I hit an edge, right? And so that already is not happening the way a physical objects don't stop when they hit a wall. They maintain momentum in the directions where the wall wasn't, right? They have that effect. And so I want to see that happen to the object because it feels so much better to have that actually happen. And so yeah, so I highly, highly, highly recommend that no matter what your end goal is, start with the closest real physical equations that you can find to what you're trying to do, and then back off them as necessary to get the effect you want. Don't go the other way around, which is try to start just typing stuff in and hoping that you end up with something good, because I see that fail so often that I think there's a real risk there of jeopardizing the whole game because you don't get that feel of the primary motion correct. And again, like I think I said in a previous stream, if you don't get that feel correct, nobody's going to play your game long enough to find out the other good things you may have put in it. Your game design may be great, but if it feels awful to move the character around, people are just going to like open it up and play it for a couple seconds and go, this feels terrible, and then shut it off, right? And like, you know, whoever's, you know, you try to submit it to a competition or something, and the judges play it for 5 seconds and they go, oh, these people clearly just don't know what they're doing, we don't need to play anymore, right? And so it jeopardizes the whole game if you don't nail the compulsories, right? If you don't like basically just absolutely get those basic things that everyone should get right, if you don't get those right, you risk ruining all the other things that you may have done really well. Like you may have a lot of great ideas that happen at a higher level in the game, and if you can't get that core second to second feel right, you risk throwing all of that work away and having a game fail that could have been a success, right? And that could have been a lot of fun for a lot of people to play. So I can't stress it highly enough that like learning how to do really good physics-based programming, which doesn't mean simulation, it just means understanding the basic equation of motions and getting them right, is a really, really powerful tool, and I highly recommend that everyone learn it. And you can break the rules as much as you want to once you learn them, but just don't not learn them, because I think it will have a lot of really negative consequences for you when you're actually trying to make stuff feel good. Why not add an opposite directional deceleration based on V when collisions occur? Doing this slowly would allow the character to reach the final pixels close to the wall. Well, so we're going to be doing collision, and what happens around walls is very important, and so we'll be spending a lot of time on that a little further down. So hold that thought for when we actually start working with the wall stuff. Are you concerned that actual physics will detract from the purity and elegance of the world's greatest jump code? For those of you who haven't been with us the whole time, I was throwing something in to demo something very early in the stream, and I made this thing where I just threw a sine controller onto some, you don't even want to know what I did, but it was awful. And I said, I said, don't ever write this for jump code. Yes, I am afraid, I guess, that it might detract. Gosh, I hope it doesn't. Let's see here. What would you need to store if you wanted to reverse time a la Braid? Well, that's kind of an open-ended question, so it's hard to say, but it does relate to physics very directly, and so I'll point this out. So the rigid body dynamics simplification, remember I said we were doing rigid body dynamics, which is a simplification of physics that basically says, all right, I've got some collection of atoms, right, that makes up, you know, this block that I want to simulate. And I'm going to simulate it by reducing it down to its center of mass, which is some position inside it, and its orientation, right? I'm just going to say that that's what I've got. And I'm going to simulate just that center of mass and that orientation, and I'm going to assume that all the atoms in the block just obey that and get moved along with it, right? That's the simplification. In that simplification, a lot of things just aren't real. They don't work the way that they normally do in terms of the microscopic level, because we're making a bunch of simplifications. And the eye can't see these differences, right? The reason rigid body dynamics is so useful is because it captures basically all of the interesting things that happen when non-deformable objects do stuff. Now there's deformable body dynamics which allow things to squish and do other sorts of things, and that's a separate thing as well. It's another simplification, but ignoring that for a second. So the reason that we use it is because those equations of motion capture all of the things that our eye is used to picking up on, and we go, oh, okay, good, right? But one of the consequences of it is that it's non-reversible, right? So you cannot, for example, take the state of the world, flip all of the quantities, and run it backwards and get back to where it was 15 minutes ago. And that's not because of our piecewise approximation, right? Our piecewise approximation is another thing that I'll get to in a second. But I'm actually talking about the actual non-participatory, if the user wasn't even controlling someone, the actual non-participatory rigid body dynamics are simply non-reversible. And the reason for that is friction. So basically what happens is when something slides along the ground or when it hits air resistance, whatever, energy is lost from the system and things slow down. Now in the real world, that's not true. There's all sorts of stuff that happens in physics, and I don't pretend to know all of this stuff, but like, you don't really have stuff just slow down. It produces byproducts like heat that are, transferring atoms, like all of the quantum physics is happening. There's all this stuff that's happening. So to say that it was non-reversible is a very different statement, and I think it may actually be reversible. I don't even know. I don't know where physicists are on that kind of stuff. They come up with new theories, who knows? But what we do know is our simplification is very non-reversible, because basically what happens is the state of the world, let's say this was a die. Let's say this block was a die, a die that you play, craps with or whatever. You roll this die, it comes to rest on the table. That's the end of the entire information you have. So when that die, it bounces, it comes down here, it bounces, rolls, and lands here. If I wanted to get back that motion, if I wanted to reverse time to when the die was in the guy's hand before he rolled the die, well, I've got no information to do that. His velocity right now is 0. I can't negate it and have him move back to where he was. And so that non-reversibility means that in order to do like braid-style rewind, like you were asking, you actually have to store the state of the world at least at key junction points, like when things stop and when they're not in free-form ballistic phase motion, where you know that you can just play it forwards and backwards and it'll be the same. So anytime there is friction, you have that problem, because energy is being lost from the system and not accounted for anywhere else, right? Another way to do it would be to record the friction forwards and then play it back, whatever. The way Braid actually does it, I think, is just with compressed records per frame. Like, I think he actually just compresses like a rewind stream and plays that backwards, I believe. I don't remember how John ended up deciding to do that. But we would probably have to do similarly. Like, we'd probably have to do something where we stored records of guys' paths, because these things are non-reversible. You can't just play them backwards from state to state. You have to actually know what happened to the guy in the past, because the system is lossy. Let's see. Is the character a bitmap? Yes, the character is. We showed asset loading like last week ago, I believe, and we loaded him in. He's actually 3 bitmaps. You'll see, hopefully maybe by the end of the week, but if not by the end of next week, he'll also be kind of bouncy, because he's made in separate pieces, and so he can kind of bounce and stuff. So we'll be doing some more with that. Let's see. Are we going to normalize the vector from the input instead of just having a special case for diagonals? Yes. Well, probably. I mean, I guess we don't have to, but that's how I would normally do it. We didn't do it that way because we hadn't gotten to normalization yet. So you're kind of jumping ahead of us. But yeah, we will at least start normalizing things pretty soon in some circumstance, but yeah. Will there eventually be a map function to help determine terrain for friction and object collisions? Probably. I haven't super decided what I want to do in terms of whether there should be a lot of slidey stuff or slowing down kinds of stuff. But that's typical of these sorts of games. So it's kind of in my head that we will have stuff like that, but I haven't specifically thought of what would be super cool about doing that. So I don't know yet, but probably. You frequently say that you like names to be descriptive and you shorten them when you use them often. It seems like you use float32 or int32 much more often than vectors. I'm wondering why v2 instead of vec2 or vector2. The answer is actually habit. These days, I probably would prefer switching to i32 or u32 because I would like those to actually be shorter. And I just haven't done that yet. But that's probably would be better. Why not break a lot of the super long code out into methods with reasonable names? I know it's C, but it's pretty spaghetti-like. So the reason for that is because we haven't decided what those functions should be. One of the things that a lot of people often do is they break things into functions prematurely. So the thing that I'll point out here is that this only gets done once. So the only point in breaking into function is to make it more readable by introducing a name like update player position, right? But we don't know if we actually want an update player position function yet, because probably we'll be wanting to use this sort of stuff for updating more than just the player, right? But we don't know what that's going to look like because we haven't added a monster, and so on. So I try to really emphasize not breaking things out into functions until you know what they're actually supposed to do, and then you break them out into functions. There's nothing particularly spaghetti about it. Like, what's the spaghetti part? It's just a lengthy function. It will do nothing differently when I move it out into a separate function. It'll do exactly the same thing. So thinking somehow that it created spaghettiness by having it in one function and that it's less spaghetti to move it out is also a bit of a false idea. In some sense, all you've done is made it harder for people to read the code what it actually does and made it easier for them to read the code what it semantically does, which is sometimes a good trade-off to make, but it doesn't make the code any better. Shouldn't you use a max speed variable? Well, I don't know. That depends on what we want to do. Maybe, maybe not. Maybe we want the player to not really have a maximum speed. We want them to be able to go as fast as they want to, subject to a bunch of forces in the environment. So if they happen to float out into space somehow in some level of the game, they could just go as fast as they wanted to because there'd be no friction. So I don't know. A max speed variable is kind of an artificial construct, and I don't know that I particularly think it's all that interesting. Let's see. So somebody says friction negative acceleration based on current velocity would feel much better in my opinion. But that's what we did. I'm not sure what you're talking about. That is exactly what this is. That is the friction. That is a negative acceleration based on the current velocity. That is literally this line of code. So I'm not sure what you're talking about exactly, but yeah, if you could be more specific about what that question was, that's EB0WER. I could address it. Can you derive the 1/2 AT squared part of the position equation again? I didn't quite follow the integration derivation flow. Sure, and in fact, I can do it in either way. I did it kind of the cheesy way because I'm not I'm not very good at integration. So usually the way I remember stuff is to do derivatives. I always remember how to do derivatives and I do those first, but I can do it actually either way. I'm not so bad at integration that I couldn't do it either way. So here's the derivative way, and here's the integration way. Okay? So doing it the derivative way, would basically be saying, okay, I know that I essentially have the function for position is going to equal something, right? I have some acceleration times the squared. I know that it's going to be a squared. I know that it's going to be a squared time term. And the reason that I know that it's going to be a squared time term is because I know that I'm going to take two derivatives. And each time you take a derivative, you lose 1 power of t, right? So I know that in order for the a to still exist down here, it would have to start out with t squared, right? Again, just talking through my thought process on how I do these. So if I have acceleration times t squared, I know I'd have velocity times t, and I know I'd have the old position, right? So f of 0, if you want to think of it that way, right? Or p, right? So whatever the position was at time 0, that's what I've got here. So I know that I'm going to take the old position, I'm going to add the velocity times time, and I'm going to add the acceleration times t squared, right? So if I actually just go do derivatives on this now, take the derivative, I would get 2at, right? That's the derivative of this term, plus v, right? The t goes away, plus nothing, because this has no t in it, so it disappears entirely, right? Take the derivative again, the v goes away, and I'm left with just the 2a, right? So that's just straight derivatives going down, right? And what you'll notice is when I get to the bottom here, I've got 2a. So if I was to use this as the equation of motion, I would always have to think about my acceleration as actually being half of what I actually am going to use to plug in. And so really all I'm doing here when I say the 1/2 at is I'm saying, okay, let's pre-divide this by 1/2 so that all the equations can be just in a as the thing that I plug in as my acceleration, right? That's what actually I was doing in my head in order to do the derivative. Now, the cleaner way to do this, if you actually know how to do math, which like I said, I don't, is to just remember how to do integration. And so to do because that's the way you'd like to be able to do it. If you're a math person, it's good. You just say, I know that I've got an acceleration. I now want to determine what is the velocity, right? So you just have to integrate it up once. And in order to integrate up something once, remember you raise the power of t1, right? So you're going to get an at, you raise the power of t1, and then you add a constant, right? Which is whatever was there that got knocked out when we did the derivative, right? And again, that's whatever the starting velocity was, right? This I should probably write this better. This is f prime of 0, right? And this is f prime of 0, right? So velocity is that, just so you know. I can keep writing it this way though, so it's easier to write. So there we go. Yeah, I guess I should just say f of 0 equals p, f prime of 0 equals v, f double prime of 0 equals a, right? Position, velocity, acceleration. And I kind of use them interchangeably, which again is not, math people would not probably like how fast and loose I play with that. And again, like I said, it's because I'm not very good at math. So in my head, they all kind of get jumbled. I think of them as both ways. I think of them as a function that's getting derived twice, and then that's having its derivative taken twice. And then I also think of it as position, velocity, and acceleration, right? They're all kind of mixed up in there. So anyway, I take the integral once, and then I need to take the integral again, right? And so again, you have to do that process in reverse. You have to say, okay, this obviously is going up to t squared, which means that I was multiplying by 2, so that means I have to divide by 2 to find out what the coefficient is this time, which is the 1/2. This guy has to have his power of t raised again, so there's tv, right, integration, and then there's the constant, which again is the old position. So this is actually the cleaner way to do it, is to just start with the a and go up, right? But I have a hard time remembering how to integrate sometimes, so I like to just do derivatives down, and then it's clear how you do them. If I think about doing the derivative in reverse, I can remember how to integrate, but if I don't, I can't, so I don't know. So that's it. So hopefully that's pretty clear how that works. It's pretty straightforward, and if you don't know how to do this stuff, Thomas and Finney is your go-to location. Buy this textbook. It is an excellent calculus textbook, and you can learn how to do all the calculus that you want to do. I feel like it even has Lagrange multipliers. One of my favorite things ever, Lagrange multipliers. All right, but we're not going to talk about Lagrange multipliers right now. Okay. Do you feel something like bullet or box 2D of player movement is appropriate? Every time I've tried it, it's been too fiddly to get stable response. Yeah, I mean, I don't know much about those specifically, but that I I share your concerns. A lot of times when I've had experience with physics code that was supposed to be like full physical simulation kinds of code, I find that it is pretty fiddly. And so usually, and especially for a game like this, where it's an action-y kind of game that's not supposed to be simulating a bunch, like there's not going to be crate stacking puzzles or whatever, right? What I tend to do is I tend to, like I was sort of suggesting is a good idea there, I try to start with a sound physical basis for what I'm doing so that I know that my motion will be mostly correct, and then I back it off to be whatever I wanted to happen in gameplay, and I find that that's a really good approach. Using a full physics simulator to do stuff, while it has some advantages, I find that they are oftentimes, like you said, very unreliable, very difficult to control. They can be crashy, they can have a lot of bugs in them. Just by the nature of physics, it's not necessarily because like Bullet or Box 2D is bad, it's because physics simulation actually to do everything right and to get everything correct is actually very difficult. And so there's just a lot of drawbacks there. And so if you can come up with ways of getting real physics into something that is itself not a full physical simulation, that can often be the best of both worlds. But sometimes you don't have that option because sometimes you really need, if you're trying to do stuff with all that real physical object interaction, sometimes you really need full physics, and then you gotta have it. Let's see. When would you want to use other integration methods? I've read Euler is great for everything. So actually, isn't this already Euler? This is forward Euler. Are you thinking of backwards Euler? All right, so those are numerical integration techniques. So we can start with that. And also, this is actually not really integrating in any particular way like the sort of stuff that you're probably thinking of, where you have to take large solutions of things. Let's table that for some other time, because that's like that kind of question is probably best left for when we have something a little more complicated that we might actually want to consider something like backwards Euler for, which I don't know if we're ever going to get to. But basically, like, stable numerical integration is not necessary for what we're doing right here, because we're never going to get into a situation where this wouldn't be stable. And so thinking about things like the choice of integrator is not particularly important. And so I just don't know if that's ever going to be within the scope of what we're doing. But yeah, it's a good question. Oh, and then I hit return and find out that he wanted to correct that question to, I've read Euler isn't great for everything. That makes more sense. I was like, why are you saying that we're not doing Euler? I'm like, we're doing a forwards Euler. Maybe you're thinking of backwards Euler. I don't know. Okay, so let me address that slightly then, because I can answer your question a little bit better if that's what you're thinking about. So the reason that sometimes you have problems with integration systems is because they can get out of control very quickly. So the problem is, if you think about what happens here, there is a time step, right? And that time step, like I said, we're pretending starts at f0, we're running it to f delta t. And we're basically saying we have some function that says where our guy is going to be over that time step. Now what can happen is you can have certain equations of motion. This is probably not going to be one of them because of how simple we've set up things to be. But if you had a complex system of stuff that was pushing on each other or doing whatever it was going to do, you can get into situations where the function that you're trying to represent has some very critically bad behavior when you try to integrate it. And typically when you're looking at things like this, you're talking about doing integration that's not analytic integration like this. This is actually fairly analytical integration. We've actually created the full equation for position. We've just created it piecewise, and we're just flat out solving it, right? But what happens a lot of other times is you're actually doing these equations of motion as approximations to things that are actually a lot more complicated. So instead of, like, this is the actual equation of motion for the guy. This is actually what it should be, and we're just actually solving it. But if instead what we were going to do is basically point sample some set of information for this acceleration, right? Where instead of saying, well, we're just assuming that the guy holds down whatever key he holds down and the guy moves in that direction or whatever, right? Let's say that we had some really complex physics function here that was going to produce the acceleration right here. And then we're going to assume that over this time step that acceleration is constant, and we're going to solve up to see what the equations are. Well, that could be very dangerous if these equations are very stiff. And what that means, the stiffness part of it means if they have some very sharp, how should I explain this? This is really an explanation that's way ahead of where we are, so I'm trying to think of how to explain this in some kind of nice way. All right. Supposing, here we go. Supposing I was to tell you that I wanted to integrate this like function here, right? And I wanted to be able to basically say, all right, what we're going to do is we've got frame time steps, right? And I want to basically say, I want to trace out this path, but I'm only going to actually be able to sample at certain points in the path, right? And what you have to remember is the state of the world, right? The state of, if these equations of motion get more complicated, then we don't actually know what they actually look like in practice. That's when you have to go up to more fancy maths. Like I said, I'm kind of dancing around this here, but what you have to imagine is that you're actually in a field of functions, right? That basically, like, there's a family of functions and you don't know actually where the one is that you're trying to follow, okay? And so at any point in this field space, I can basically say, all right, wherever I am, tell me what the derivative of this function is. I'm going to step the equations of motion forward to the next time step, and that's where I'm going to say everyone is. And then I'm going to look again, and I'm going to look at the derivative, and I'm going to do the same thing, right? Well, what ends up happening if you have these sorts of situations where the equations are complicated enough that you can't write those simple closed form, things like what I just did, is you can see that you get into problems very quickly, because what's the derivative here? Well, the derivative points up in that direction. I step that far, and I get to my next time step, and I say, okay, I'm here, what's the derivative? Well, the derivative is this really steep thing that goes up there. I come here, and I go out to here, and I go, oh, all right, bad news, guys. We're nowhere near the old function. But I don't know that because I don't know what the function actually is. I just know it's this very complex thing that can't be analytically integrated. So now I'm here, I take the sample of what the derivative is there, and the derivative is pointing back down here, right? So basically I step down here and I get here, and you know, maybe this thing curves up again or whatever, and so I step out there. And what can happen if you're in a very bad situation where these lines kind of all go up like that, like let's say that they look kind of more like this sort of a thing, you could get into a situation where you just fly off into space and you're nowhere near the old thing that you were if you're doing forwards Euler, which is the name for the kind of integration that you do where you just sample the derivative and step forward, right? One solution to this is backwards Euler. And this is why I said, when you said I've read Euler isn't great for everything, it's forwards Euler that isn't great for everything. It's forward Euler that's not great for games. Backward Euler is actually very good. And what backwards Euler is when you go to the time step that you would next be on. So instead of doing it this way, where we took the derivative and stepped forwards, instead what you do is you go to the next time step and you search along this line, essentially, for where points back to the place that you were at. So it solves it in reverse. What that means is you can never have something out here because this guy pointed in a totally different direction, right? So what would happen when we took this time step is we'd come here and we'd look for some point in this area that pointed back to where this was, right? So it would be somewhere that was kind of like down here, right? It would be off the curve, but it would be off the curve in a less energetic place, right? So it sucks the energy out of the system and brings things back to rest when it is wrong, rather than flying them off into the middle of nowhere when it is wrong, right? And so backwards Euler is actually very good, but it's much more expensive, which is why you often don't do it. So I don't really want you to think about what we're doing as forward Euler, though, because all this stuff is stuff that is way outside the scope of what we're doing. This is numerical integration, and we're not really doing numerical integration. We're basically doing analytical integration. We're just doing piecewise analytical, which I realize sounds like hand waving because piecewise analytical, why isn't that numerical? Well, it's because I'm actually saying these are actually the equations of motion for the guy. And we just happen to change what the constants are when the user pushes the button, right? But we know what they are and we can integrate them up analytically. I just did it for you. We showed the 1/2 AT squared thing. And so we're not really doing something that falls into this category. So hopefully that answers the question there, and we're kind of way over time here, but let me just take a look and see if there's anything else. Let's see. Yes, I was going for a figure skating analogy when I said you have to nail the compulsories. Let's see. Will we use rigid body even after the hero gets his 3 parts bouncy and all that? Yes, we will. I'm only going to do the deformable stuff on him non-physically. Meaning the deformability will be purely a graphics effect. It will not be based on solving any kind of gelatinous equations to make him like, you know, gelatinous around or anything. Let's see. EB0WR. I'm sorry, I meant that you could take some constant friction and increase it exponentially as velocity decreases so that the character would stop much faster in the end of its movement without that sliding. I am running forward, I suppose, but whatever. Yes, so I do agree with you. We probably will do something different for his motion eventually that has some slightly different properties, but yeah, you're jumping ahead a little bit too much. Remember, we got to go one step at a time so we don't leave too much stuff unexplained. If we had terrain, ice, or mud, we could use that as the scalar for the friction deceleration, and with almost one additional line of code from today, we'd have something convincing, somewhat convincing interaction, right? Yes, that is absolutely correct. And that's, again, one of the reasons to frame it correctly as equations of motion and friction is because you don't have to do any extra work to figure out how those things would be. You just literally are changing whatever that coefficient of friction is. And that'll get even more true as we do sort of more physicsy stuff in there. All right, I think we are done with questions for now because we are out of time. I think I got all the ones that pertained to the actual stream. Anyway, again, if you're asking a bunch of questions that have nothing to do with the stream that we were just doing or a previous day's code, come if you want to ask the questions. I will answer them. Just come to come 15 minutes before the scheduled start time, and I will answer them on the pre-stream. Okay. Thank you, everyone, for joining me for a very mathy Handmade Hero today. I'm very happy with where our guy is now, though. It just feels so much better already. There's a bunch of things I still want to do the movement code, so it still doesn't feel as good as I want it to, but of course, we're definitely at the part where it's like, okay, I could see actually playing with this guy now rather than before where it was just awful. And so we're getting there, baby steps, and we'll make some more baby steps tomorrow, and we'll start to get into some pretty respectable territory, I think, and that's always a good thing. So thank you very much for joining me. It has been a pleasure coding with you, as always. Again, if, oops, what is that? I don't want you to save anything from here. No, discard. Discard. Close and discard. Okay, there we go. Again, if you would like to have access to the source code, you can pre-order the game on handmadehero.org, and that gives you full nightly access to the source code, which I update every time after we're done coding. So if you're interested in that, all you have to do is pre-order, and you can download it anytime you want. Follow along at home. Try playing with the code yourself if you want to make changes and see how they work. That's also pretty good. And it comes with the art assets as well. For the all the stuff that we use on the stream for development are included in there as well. So that's kind of fun too. So, you know, when you try stuff out at home, it'll actually look like it does on the stream. We also have a Patreon if you want to support, or sorry, Patreon. If you want to support the video series, you can click on that link and subscribe in there. And we also have a cool site that a lot of people have spent some pretty significant time making pretty awesome. There's the news and forum site. If you're trying to learn from the stream, I highly recommend it. There's an episode guide, newly updated episode guide actually. So it's got a nice index page now that's got some cool stuff on it too that we've now synchronized. It's pretty sweet. A lot of folks up here that you see in here have done a lot of really great work on it. So if you're trying to catch up with old episodes, I highly recommend going in there. It's got some great stuff. If you click through on the episode, it's got like time-coded jump markers and all this stuff. It's really awesome. There's a coding resources page where you can look at ports to Mac OS X or Linux if you're interested in that sort of stuff and other sorts of things you might be interested in. And finally, there's a a code discussion forum that you can jump to where you can ask questions and stuff like that if you're having trouble or if you just want to talk about something that we've done in a little more detail. So I highly recommend if you're trying to learn from the series to check that out. It's a great place to go. So thank you, everyone. Tomorrow, I believe, is today Thursday, I want to say. Is that true? No, today's Wednesday. So we've got one more day. We've got tomorrow at 8 p.m. Pacific Standard Time. So I will see you here tomorrow at 8 p.m. Pacific Standard Time. And then Friday, of course, is early morning stream. That's a 9 a.m.er, so I usually see these folks in Europe at that time. But tomorrow, I hope to see you all again, 8 p.m. Pacific Standard Time, for some more player movement code. And now that we got the equations of motion out of the way, I think it should be simpler for us to kind of do a few more things in shorter order. So thank you, everyone, for joining me, and I hope to see you tomorrow.